Greetings and a warm welcome to everyone present here. My name is Huang Xin, and I am the proud proprietor of SLAM of Daotong Intelligent Aviation. In today's session, I am excited to delve into the fascinating world of SLAM technology and its innovative application in the realm of drones. Our discussion today will be structured into 3 comprehensive segments. To kick things off, the initial segment will offer an in-depth overview of SLAM technology encompassing an explanation of its basic operational principles. We will explore the various classifications, highlighting the strengths and weaknesses inherent in different methodologies. Following this, we will seamlessly transition to illustrating how SLAM technology is ingeniously integrated into our company's drone products. I will elucidate on the current standing of our SLAM technology capabilities. Concluding our session, we will gaze into the future of SLAM technology, pondering over the potential advancements and the strategic directions our dedicated SLAM technical team might pursue moving forward. Diving into part 1, let's demystify SLAM technology. At its core, what exactly is SLAM? In Mandarin, it's referred to as simultaneous positioning of one piece. This concept primarily involves the utilization of sensor measurements. Without relying on pre-existing, detailed information about the surroundings, the technology enables an entity to construct an environmental model in real time as it navigates, simultaneously estimating its own movements in the process. Generally speaking, you can imagine that the aircraft is in a complete current environment. It can determine its current movement and its position through the information of the surrounding environment. This is positioning. At the same time, it relies on the surrounding information on which it relies for positioning. It is a map. During the flight, the aircraft will continuously model and record the environmental map. This process is that the status and the sword map are carried out at the same time. They interact with each other to correct the status information to help better cut the map. It can help with better positioning, so they are a complete and tight system. Why do we need SLAM? Because drones are now moving towards a stage of becoming intelligent. What we want to achieve is a truly autonomous flying aircraft that does not require a remote control. We must go to realize perception and positioning by yourself. It may be said that with GPS, it can still complete positioning, but it is not. The same route with the arrow map function cannot be exactly the same when flying under GPS positioning. However, if there is a SLAM map, this can be achieved. With the help of the SLAM map, the aircraft can achieve more accurate positioning at the same time. In some circumstances, this is not possible, such as when the GPS is lost or the GPS is interfered or deceived. Therefore, SLAM is an indispensable key technology for drones to move towards more intelligent wiring. Generally speaking, SLAM is WAMing. The workflow is as shown in the figure. The sensor data is input to the front-end odometry for adjacent time position estimation and local map collusion, and then transmitted to the back-end for optimization and full-level mapping. Because the front-end odometry is a map process every time, it is estimated that there is a certain error. After a long period of estimation, a relatively large drift will occur. Then, the phenomenon you may see is that when the aircraft orbits, after a large circle, it cannot accurately return to the origin. In order to eliminate this accumulated error, the loop detection module is necessary. As the name suggests, it detects whether the aircraft has visited the place it passed before. If a loop is detected, it will be passed to the rear. The back-end optimization will adjust all positions or map points on the entire back-end to build a map with overall consistency. Such a map will then be given to the front-end odometer for positioning. In this way, the front-end odometer will be able to obtain unlimited TFLS. The drifting position, so positioning and seeing pictures, is a complementary process. This is a basic workflow of SLAM. According to the type of sensor used, it can be divided into visual SLAM and laser SLAM. Then it is used according to the server. The inertial measurement unit IMU can be divided into visual inertia SLAM and laser inertia SLAM. IMU will be used in the SLAM system because IMU has a relatively high frequency. Generally speaking, the operating frequency is from 100 Hz to 1000 Hz. Its cost is relatively low, and it can complement low-frequency image data or laser data. In addition, it can measure. Absolute scale information can be obtained from acceleration and angular velocity. High integration accuracy in a short time can improve the accuracy and robustness of the SLAM system. For visual SLAM, its sensor is simple, cheap, and small in size compared to laser SLAM. It is easy to arrange and install. The calculation of image data is small. The height of resource small work is relatively high, so it has obvious advantages when applied on drones. If your main purpose is to build more detailed 3D models or aero diagrams, laser SLAM will be a better choice. The following will mainly introduce our visual SLAM plan. Our SLAM main words. The sensor input is multi-channel binocular image data and IMU. Taking our Evo Max as an example, we support the input of its front, rear, up and down binocular images. Our upper method will support dynamic and confident adjustment to use pull. Several channels of images and their image frequencies also support online calibration of the internal parameters of the camera IMU and calibration of the external parameters of the camera to ensure the accuracy of the calibration parameters during long-term use. Other modules are similar to the general SLAM module. Specifically, different implementation methods are used, such as whether the status update uses the filter method or the optimization method. In the end, whether the image uses optical fluidization or the matching method based on the description paper. In the end, we will output the position of the aircraft at high frequency for use. Aircraft control and mission navigation. At the same time, we also support saving the SLAM map if the same scene is used next time. When flying, such a map can be used for better positioning next time. This is a visual SLAM when running on our Arowana aircraft. The picture indicates a trajectory of our sword map. The yellow dots are features in the map. This map is different from the popular mobile phone navigation maps we usually see. It is mainly used internally by SLAM. It uses the map that SLAM knows internally. If SLAM is used, it can be recorded based on these map points to complete the map-based positioning estimation. In addition, this test was conducted at an altitude of 300 meters and flew for 35 minutes, which also proved the stability of our SLAM system under long-term operation in order to evaluate the accuracy of SLAM. We usually compare the velocity position of SLAM with the increment of RTK. The picture shows one of our data sets and the velocity position of RTK. The outcome of comparing positions on the left side indicates a discrepancy in the velocity and frame values across the 3 dimensions, which all seamlessly integrate. Subsequently, we are set to present how our SLAM, simultaneous localization and mapping technology, is applied to drones. Primarily, it targets indoor environments where GPS is unavailable. Thanks to the SLAM system, drones can perform standard indoor flights and maintain hover, enabling us to embark on various industrial uses. Examples include the automated inspection and surveillance of indoor storage facilities, along with other missions designed to facilitate automated operations and consistent daily checks at designated points. The aerial capabilities of drones allow for the execution of tasks across multiple levels and areas, surpassing what traditional patrol systems offer. Another significant advantage is the substantial enhancement in the efficiency of inspecting aircraft, a task that proves challenging for conveyor-type or roaming inspection robots to accomplish. The second practical use case involves flying outdoors without the assistance of GPS technology. We are capable of achieving distances of 300 meters to 5,000 meters in non-GPS flight conditions. Here is a comprehensive video presentation of our flight without GPS. It thoroughly demonstrates the entire operation of the aircraft in a visual mode. Thanks to SLAM technology, our outdoor flying becomes both safer and more intelligent. Even in the absence of GPS, or if GPS signals are being jammed or disrupted, our aircraft remains capable of safe flight. In our experiments, we employed anti-drone technology to disrupt the image transmission signal, illustrating how it gets disconnected due to such interference. Despite the lack of GPS signal, our aircraft is unaffected because the jamming device cannot disrupt the SLAM system. SLAM operates based on internal sensors, offering a significant advantage over GPS reliance. This advantage lies in the fact that it grants us autonomous control over the aircraft, putting the power directly in our hands. The third feature we offer is the ability for one-click, precise return-to-home functionality. We can achieve centimeter-level return-to-home accuracy. We can first take a look at this test video. This was taken by hand during the test. You can see that when the aircraft finally landed, its landing position was consistent with the previous takeoff point. The traditional GPS can also achieve return to home, but when it comes to GPS positioning accuracy, the return to home accuracy often has an error of several meters. It cannot achieve centimeter-level positioning errors like ours, because our aircraft will locate all previous areas during the return process. The map ensures the consistency of the overall positioning and truly realizes one-click return, instead of needing manual control to eliminate GPS errors or worry about the aircraft landing in other unsafe places during the return process, which greatly provides operational convenience. The 4 applications are accurate repeat shots. As the name suggests, it is to repeatedly shoot a certain point of interest with a posture or angle. The interesting thing is, for example, we record a certain point of interest during the flight, and then when we need to come back and take another photo of this point, we can directly use this precise review function to accurately return to the previous position. This can be achieved. The basis of the function is still SLAM, because we have recorded the map that the plane has flown during the flight. It is not difficult at all for SLAM to return to the previous position. It is very simple. We then retract to the first point indoors. As an example of warehouse inspection, we can set our points of interest in the inspection function. Let the aircraft take pictures at regular times and fixed points every day, and then use the images to analyze whether it has abnormal working conditions, thereby achieving 24 hours of unmanned monitoring. Operations LAM has become the basic configuration on our aircraft. Our aircraft are also widely used. The aviation science and technology industry has flooded a large amount of value for enterprises and society. The last value is SLAM. The future development and prospects of technology are also some of the things we're doing recently. The first one is SLAM in dark conditions. Nowadays, ordinary cameras cannot work in dark night conditions. We are trying to use infrared cameras and night vision. Sensors such as cameras and mirror cameras are used to obtain image data in dark environments, and then based on this, we make SLAM, turning SLAM into a system that can work during the day and night. The second one is the ultra-high altitude SLAM. The working limit of SLAM is 300 meters. Then this is far from enough for some scenarios. We also need to improve our working range to support 5 GPS flight at an altitude of more than even 1,000 meters. The third one is the offline aero map, optimization and multi-machine joint aero diagrams. Online aero diagrams will be considered due to limitations in computing resources and time, which will cause some loss in aero diagram quality. We use frontline optimization of the sword map to improve the quality of the sword map. At the same time, we can use our autonomous network technology to achieve multi-machine joint sword maps to improve the efficiency of the sword map. Finally, the combination of SLAM technology and deep learning has already been used in academia and industry in this regard. We have done a lot of research, such as using deep learning to perform feature matching and tracking, ghost detection and depth estimation, etc., as well as end-to-end SLAM directly from data input to unknown estimation. These are the directions we are looking forward to and paying attention to. That's what I call sharing today. Thank you for listening.